Stokes theorem. Stokes theorem is remarkably important. Stokes theorem was what allowed Maxwell to notice a hole in electricity and magnetism, plug that hole, and lead to Maxwell's equations. Maxwell's equations were what then went on to inspire Albert Einstein to do his theory of relativity. Kind of an important thing for us to understand. So when we have Stokes theorem, what we have is the integral of the curl of some vector field dotted with a little tiny infinitesimal area dA. Now curl is the amount that goes around. So because it's the amount that goes around, we look at the amount that's going around on this vector field. And if we look at the next region of space over, the next dA, that dA will wind up being going like this. And then the next one would go like this. And what we notice is that at every point in here, even if we did another one down here, we would see something that looks like this. These combine together and cancel out. Kapow, they're gone. Kapow, they're gone. Kapow, they're gone. And this leaves us with an overall region of space where all of our internal curls are canceling out, and we're just left with what our function was at the boundary. So we must have a closed loop of V evaluated at the boundary. This is just the fundamental theorem of calculus come out again, this time applied to curls. We are taking the integral of a derivative and evaluating that function now at the boundary that we have. Here's our vector field. V is equal to 3y minus 2x x hat plus x squared plus 4z y hat. What we're going to do in this video is we're going to go ahead and show that the line integral around the outside is going to be equal to the integral of the curl of this vector field dotted with dA. We're going to show Stokes' theorem is true for this particular vector field. Okay, when we do this, let's start with this side. We're going to have our 4 different line integrals, and the particular area we're going to do is a square in the xy plane, and this square in the xy plane, so square in xy plane of edge 4. So x, y, z, and we have a square where this is 4 and this is 4. Okay? We're going to break our integral up. So this closed loop line integral can be broken into 4 smaller integrals. So we have the integral, v dot dl, is going to be the integral from here to here. So from x equals 0 to x equals 4. And all the way along here, y is going to equal 0, and z is going to equal 0. Well, our dl along this path right here is just going to be dx, so we can say that v dot dl is going to be 3y minus 2x, x hat plus this dotted with dx x hat simplifies to this. Now along our second, we're going from, so we've done this, now we're going from here to here. Well, x is going to equal to 4 all the way through. Y is going to go from 0 to 4. And z is going to wind up staying 0. Now, because our change is in the y direction, we have a dl is equal to dy y hat. When we take v dot dl, this will only maintain the y component. So now we have x squared plus 4z dy. Now we're going to go from here to here, a little confusingly. X is going to go from 4 back to 0. Y is going to stay constant at 4. And z is still going to stay 0. And just like we had over here, our dl vector is still pointing in the positive dx direction, even though our path is going back this way. That's taken care of in our limits of integration, going from 4 to 0. When we do this, we dot it with our dl with our vector, we're left with only this. So once again, we have 3y minus 2x dx. And our final little piece is going to go from here to here. So along that path, x is going to equal 0 the whole way. Y is going to go from 4 to 0. And z is going to, of course, stay 0, as it has been all the way through, because we're in the xy plane. Once again, we've got our dy, so we pick up an x squared plus 4z dy. Now, because our x and z are all 0 here, this entire integral will vanish. So this integral has gone away. When we take this integral, because y equals 0, we can say that this term goes to 0. Here, z is equal to 0, so this term will go to 0. X is going to be equal to 4. So when we, let's deal with this one first. So we're left with the integral of negative x dx going from 0 to 4. So that's negative x squared from 0 to 4. Plus this integral, x is going to equal to 4 all the way throughout. So that becomes 16 y, where y is evaluated from 0 to 4. And then here, y is going to equal to 4. So this becomes 12 minus 2x. So this becomes 12x minus x squared. And now we're evaluating this from 4 to 0. And we've already said that this one is 0. As we plug all of these things in, this becomes minus 16 plus 64, 0, minus 48, minus negative 16, becomes plus 16. And then of course that 0 can just go away. These terms can go away. 64 minus 48 is 16. We now have shown that this side is equal to 16. We'll do this side instead to show that they're equivalent. So we start once again with v, but this time what we're going to do is we're going to calculate the curl of v. Now, of course, you can do with this with Levi-Civita notation and so forth, but I find it easiest to calculate the curl as the determinant of a matrix if I'm doing it in Cartesian. So here we have the x component, 3y minus 2x. Here we have the y component, x squared plus 4z. And here we have 0. And we go through and take out our determinant, and we are left with 0 minus the derivative with respect to z, so minus 4x hat, and then negative 0 minus 0, so plus 0 y hat. And then for our z hat component, we have the derivative here, so that's 2x, and then we have the derivative this way, which will be minus 3y z hat. When we are taking this particular integral, though, we're taking dot dA. We have to ask ourselves, what is the dA? Well, we use the right-hand rule to curl all the way around our boundary, and we see that our dA, our area integral, will point in the positive z hat direction. So dA vector is going to equal dA scalar times z hat. So this expression right here is going to be the integral of minus 4x hat plus 2x minus 3y z hat dotted with dA, and our dA can be thought of as a little tiny square of length dx and of width dy. dx dy z hat. So that means this term winds up going away. Our limits of integration for x are 0 to 4. Our limits of integration for y are also 0 to 4. So we have 0, 0, up to 4, 4. So this is going to be equal to 0, 0, 4, 4. 2x minus 3y pardon me, I made a little mistake. This is 2x minus 3. So that's minus 3. That's minus 3. dx dy. So that's going to be x squared y minus 3xy evaluated from 0, 0 to 4, 4. So plugging that in, we have 4 squared, which is 16, times 4, which is 64, minus 3 times 4 times 4. 4 times 4 is 16, times 3 is 48, minus 0 is 16. What this video showed was a particular vector field that we had right here, and we took the line integral around our square and showed that this line integral around our square was equal to the curl, and then we take the integral over this entire area of that curl. This was an example of Stokes theorem. This idea will be used in later videos to show when we can say that integrals will be path independent.